Looking at section 5.3, we have double angle, power reducing, and half angle formulas. So we are going to use the double angle formula, use the power reducing formulas, and use the half angle formulas. So let's take a look at the first one. We have our double angle formulas. And again, if you look on your trig cheat sheet, your formula sheet that you have, all of these are listed on there. Cosine has a couple variations than just the one that's listed right here. So first off, we have that sine of 2 theta. That's going to equal 2 sine of theta cosine of theta. The second one is our cosine of 2 theta. The main one is to have a cosine squared of theta minus a sine squared of theta. And as I mentioned, there are multiple cosine of 2 thetas that have different formulas that could be used. We'll look at those in a moment. And then the other one for our tangent of 2 theta is equal to 2 tangent of theta divided by 1 minus tangent squared of theta. So let's look at an example. Using that double angle formulas to find exact values. It says if the sine of theta is equal to 4/5 and theta lies in quadrant 2, find the exact value of sine of 2 theta. Well, we're going to find the sine of 2 theta, and then we are also going to find the cosine of 2 theta, and we're going to also find the tangent of 2 theta. So we're going to use all three of these with this one example. So given that we have a sine of theta is equal to 4/5, we have our y value of 4 and our radius of 5, we can identify our x value easily by knowing that that's going to end up a -3. You should be able to identify the 3, 4, 5 triangle, and since we are in the second quadrant, the x value has to be negative. So you could use your Pythagorean theorem to solve that down, or just logic of knowing you have a 3, 4, 5 triangle. So our x value is going to be a -3. Now, as I said, they gave us what the sine of theta is. That's a 4/5. And then we can identify our cosine of theta by taking our x value, which we just said is a -3, divided by our radius of 5. And now we can go about finding our sine of 2 theta and our cosine of 2 theta. So sine of 2 theta tells us that we're going to equal a 2 times our sine of theta. A sine of theta is 4/5. And then we multiply by the cosine of theta, which is a -3/5. And if we multiply those all together, numerator-wise, we have 2 times 4 times -3, so we have a -24. And denominator, 5 times 5 is 25. If we find the cosine of 2 theta, that means we're going to take cosine squared of theta, which means that we're going to take our cosine value, -3/5, and we're going to square that. And we're going to subtract our sine squared of theta. Sine is 4/5, so we're going to take 4/5 and square that. So if I square a -3/5, that gives us a 9/25. We're going to take away a 4/5 squared as a 16/25. And if I simplify that down, 9 take away 16 is going to leave us with a -7/25. So we have our sine of 2 theta, our cosine of 2 theta. Let's find our tangent of 2 theta. So again, our given was our sine of 4/5. The cosine we found was a -3/5. We can find our tangent by taking our y value, which is 4, divided by our x value, which is -3. And then we can go about plugging it in. So we have a 2 times the tangent of theta. Tangent is 4 over -3, or just a -4/3, divided by a 1 minus our tangent squared of theta. Tangent is -4/3, so we're going to take -4/3 and square that. We have a little bit of work to do, so I'm going to kind of come over here and use this space a little bit. So if I have a 2 times a -4/3, that's going to give us a -8/3. On the bottom, I have a 1 minus. -4/3 squared gives me a 16/9. Now, if I'm taking 1 and I'm taking away 16/9, I would need a common denominator. So I'm going to call that, instead of a 1 minus, I'm going to call that a 9/9 minus. And if I have a 9/9 minus a 16/9, or 16/9, we end up with a -7/9. And we have that -8/3 that's being divided by that -7/9. And we could do a little, keep the first, multiply by the reciprocal. And if I simplify that down, let's see, negatives cancel. 3 goes into 9 3 times. So it looks like we are left with an 8 times 3, which is a 24/7. So that's what our final answer is going to be for the tangent of 2 theta. And as I mentioned, there were multiple cosine of 2 thetas. So these are the other These are the other two pieces that they also have on that formula sheet for you. So other variations are cosine of 2 theta is equal to 2 cosine squared of theta minus 1. And then a cosine of 2 theta is equal to 1 minus 2 sine squared of theta. So depending on what you might be trying to verify would determine which of those formulas you'd want to use. So let's do another example. So we are going to verify the sine of 3 theta is equal to 3 sine theta minus 4 sine cubed of theta. And they want us to take the sine of 3 theta and start breaking that down. Well, if I have a sine of 3 theta, I can use what we did the other day with our sum and difference formulas that we had. So if I have a 3 theta, I can break this into a sine of 2 theta plus theta. 2 theta plus theta gives me my 3 theta. And that's going to allow me to eventually start using what we were looking at today with those double angles. But in the meantime, let's go about using our sum formula. And if I have a sine, that means I'm going to have the sine of the first, sine of 2 theta, cosine of the second, cosine of theta. And I'm going to add with that the cosine of the first, so cosine of 2 theta, and then the sine of the last, or sine of the second. So that's just using that sum formula. That's what that was here. So now that I have a sine of 2 theta, well, we can use the kind of pieces that we just used today, right? Some of those formulas. So I can use my double angle formula. I have a sine of 2 theta and I have a cosine of 2 theta. So I'm going to use two of them in the next step. So if I break down the sine of 2 theta, that's going to get broken down into a 2 sine of theta, cosine of theta. And then I have that extra cosine of theta hanging out there. I'm going to add with that. Now, in terms of this cosine of 2 theta, I'm going to use the one that looks somewhat like the Pythagorean identity, the 1 minus this 2 sine squared of theta, and then I still have that extra sine of theta on the back side. Let's clean this up a little bit. So if I clean that up a little, let's see what we got. We have a 2 sine of theta cosine squared of theta. And then I'm going to go ahead and distribute this on in. Reason I'm going to distribute this is our goal is to eventually get a third power. And if I have a sine squared multiplied by another sine, that's starting to get me to that sine cubed. So that means we're going to end up with a sine of theta minus a 2 sine cubed of theta. Now let's see what else we can do. In the end, we do not have any cosines. So that means I want to try to get rid of that cosine function here. And if I have a cosine squared of theta, what can I do with that? I could use the Pythagorean identity. So let's change this up. We have a 2 sine of theta, and instead of a cosine squared of theta, I can turn that into a 1 minus a sine squared of theta. And then I have this extra plus sine theta and that minus 2 sine cubed of theta. Again, let's go ahead and do some distributive property. Let's go ahead and distribute out this 2 sine of theta. So that means 2 sine of theta times 1 is a 2 sine of theta minus 2 sine of theta times sine squared theta is going to give us a 2 sine cubed theta. And then I just have the rest of that stuff I'll bring down. Plus sine of theta minus 2 sine cubed of theta. Let's look for some like terms now. We have 2 sine of theta and we have a plus sine of theta. So altogether we have 3 sine of theta. And then I have a minus 2 sine cubed of theta, and I have a minus 2 sine cubed of theta, which means I have a minus 4 sine cubed of theta. And that looks exactly like what I was trying to get, doesn't it? 3 sine of theta minus 4 sine cubed of theta.